Assalamu alaikum. It's me, Dr. Muhammad Shoaib, and in this lecture we will study Norrish Type I reaction. Basically, this reaction comes into the category of photochemistry of carbonyl compounds. Carbonyl compounds, usually the ketones, undergo four different type of reactions, that is alpha cleavage, which is known as Norrish Type I reaction, beta cleavage or the abstraction of hydrogen from gamma carbon, that is Norrish Type II reaction, and third one is intramolecular and intermolecular hydrogen abstraction by carbonyl oxygen, that is photoreduction, and fourth one is 2+2 cycloaddition, that is Paternò-Bucci reactions. Most of these cases, these four processes are in competition, and sometimes a mixture of product is formed. So we have to be very careful by choosing the conditions and the substrate to obtain our desired product. Alpha cleavage or Norrish type 1 process. Three types of ketones, that is saturated cyclic ketones and saturated acyclic ketones, or beta gamma unsaturated ketones, give this type of reactions. First is Norrish type 1 reaction by acyclic saturated ketones. Usually the Norrish type 1 reaction is common in gaseous phase and it is very uncommon in the solution phase. The primary process is the initial cleavage of the bond between carbonyl carbon, that is, and alpha carbon to produce an acyl radical, that is, this is acyl radical, and an alkyl radical. It is a primary photochemical process. These initially formed acyl and alkyl radicals are stabilized by one of the secondary processes as shown here. The first secondary process is the decarbonylation. This acyl radical undergoes decarbonylation to produce carbon monoxide and an other alkyl radical. These alkyl radical can give a recombination reaction to produce alkanes, or there is the possibility of intermolecular hydrogen abstraction to produce alkene and alkane. Here the hydrogen from this alkyl radical is shifted to this alkyl radical, so that alkene, which is more stabilized, double bond is in between the chains, the more substituted double bond is formed. The second possibility is, here is the second possibility, intermolecular hydrogen abstraction by acyl radical. First was the decarbonylation of acyl radical, then there is a possibility of hydrogen abstraction. One hydrogen from here is abstracted by this acyl radical so that it is converted into aldehyde, as shown here, aldehyde, and an alkene is formed. Third possibility is the intramolecular hydrogen abstraction by alkyl radical. This alkyl radical can also abstract one hydrogen from this so that this ketene and alkane is formed. Remember that the main secondary reaction or process of saturated acyclic ketone is the first one, which is decarbonylation. Thus, the Norrish type I is a two-step radical mechanism, that is primary and secondary process, and formation of an acyl and alkyl radical can be proved by using a trapping agent. For example, here is a ketone, the acyl and alkyl radicals are formed. Then after decarbonylation, alkyl radicals are recombined to give alkane. And the formation of this acyl and alkyl radical can be proved by using a trapping agent. Here it is 2266 tetramethylpiperidine 1-oxyl radical, and we obtain an ester and ether, which is only possible if there is an acyl radical, ester is formed, and if there is an alkyl radical, ethers are formed. As both these products are formed, so it is proved that the primary process leads to the formation of acyl and alkyl radicals. Here is another example. Here we have two types of ketones, which is A and B, and when the product is observed, we have different types of products. The product 1, we say that A gives the product 1 after decarbonylation. After the primary process, decarbonylation takes place and alkyl radicals are recombined to give this alkane. And we see that this is the second one. After decarbonylation of B, the alkyl radicals are recombined to give this alkane. Here we obtain a third product, which is a cross product. As we can see that one part of this alkane comes from A and the other half of this alkane comes from the B. This crossover experiment also confirms the two-step radical mechanism. Here, in case of unsymmetrical ketones, the bond which leads to the most stable free radical is broken down. So this bond will be broken down to give the tertiary free radical. Remember that free radicals are electron deficient, and this will be the minor product. This is so stable that exclusively this will be the only product which is formed in this process. If both alkyl group of same or similar, then there is a little selectivity between the bond cleavage. Here this bond will be broken down, or this alpha beta bond can also be broken, so there is little selectivity. As we have seen at the start of this lecture, that Norrish type I is mostly favored in the vapor phase and it is uncommon in the solvent. But if there are inert solvent, so it will form a solvent cage which facilitates the recombination of initially generated radical pair. Thus, low quantum yield is obtained in inert solvents. So let's see, we have taken a solvent here, that is liquid phase, the primary process which will produce acyl and alkyl radical, and after decarbonylation both these alkyl radicals will be joined to produce an alkane. Norrish type I process is efficient in liquid phase only if a stable radical is formed. The stable radical includes allylic, benzylic, tertiary alkyl and acyl radicals. Here is an example in the liquid phase. The first one, it is the primary process. It will produce a silent alkyl radical. Then after these acyl radical will undergo decarbonylation and the alkyl radical will be joined, will recombine to give alkane. It is in 100% yield. Next is Norrish Type I reactions for the saturated cyclic ketone. Here is a summary. Cyclic ketones shows a greater tendency to undergo the alpha cleavage to provide acyl-alkyl biradical. Norrish type I cleavage of acyclic ketones takes place by singlet as well as by triplet excited state, but in cyclic ketone the reaction takes place exclusively by the triplet state. The triplet state is at least 100 times more reactive than excited singlet state, and the Norrish type I process involves the initial cleavage carbonyl carbon and alpha carbon bond, and a subsequent secondary process corresponds to those observed for acyclic ketones. Decarbonylation of acyl-alkyl diradical to give carbon monoxide and a dialkyl radical. The dialkyl radical can recombine to give cycloalkane, or it undergoes the intramolecular hydrogen abstraction to form alkene. Here we have a saturated cyclic ketone. This CH2N shows that it can be 1, 2, 3, 4 or whatever the number of carbon we have in start. In the presence of sunlight, singlet state is formed, then intersystem crossing will lead to the triplet state. So the diradical is formed, which one is acyl and one is alkyl. And after decarbonylation, as we have discussed that it is the major process, after decarbonylation there are two possibilities: either a recombination to form a cycloalkane or the intramolecular hydrogen abstraction to form an alkene, as shown here. Intermolecular hydrogen abstraction can also be done by acyl radical. If this acyl radical before undergoing decarbonylation abstracts one hydrogen from this carbon, then unsaturated aldehyde is formed. And similar to the previous one, in acyclic ketone, if there is intramolecular beta hydrogen abstraction from the acyl radical by alkyl radical, if one hydrogen from this beta carbon is abstracted by this alkyl radical, then the ketene is formed. Here the ketene is formed. In solution phase, biradical pair is mainly stabilized by intramolecular hydrogen transfer, which leads to the formation of either unsaturated aldehyde or a ketene or both. In solution phase, and this biradical is formed, and in solution phase, decarbonylation is not a major process. So only the process which is major is intermolecular hydrogen abstraction, either by alkyl radical. Here the alkyl radical abstracted a hydrogen from this carbon, beta carbon, to produce this ketene, or the hydrogen abstraction by this acyl radical from this beta carbon of alkyl radical to form unsaturated aldehyde. This ketene will react with water or alcohol or ammonia, with whatever the solvent is present here. With water it will form carboxylic acid, with alcohol it will form ester, and with ammonia or and the derivative of ammonia, that is primary or secondary amine, it will form amide or substituted amide. As we have seen that in solution phase the decarbonylation is not a major process, but in vapor phase decarbonylation and intramolecular hydrogen abstraction takes place. First decarbonylation takes place, then either the cyclization takes place or this hydrogen is abstracted by this alkyl radical to form an alkene. And in the liquid phase we have seen previous examples, which is the formation of alkene which is the formation of unsaturated aldehyde or ketene. Here there is an other possibility, which is the back recombination. That is the back recombination of starting material. Here, after the primary process, it can recombine to give the reactant again. How this is proved? This is proved by using a suitable alpha substituted cyclic ketone, and this bond is broken, and after a recombination and the epimer is formed. Here this methyl group is out of the plane, and here this methyl group is into the plane. And that is the epimer of the reactant is formed, which proves that the recombination takes place. Here is another example. Here is the reactant. After recombination, it forms the epimer, that is the configuration at one carbon is changed. And the other possibilities are, there are other possibilities. After decarbonylation, these cyclopentanes are formed, and without decarbonylation this unsaturated aldehyde is formed. Here is another example of recombination. Now let's see the Norrish Type I process given by cyclopentanone. In gaseous phase, these also undergo decarbonylation, and similarly one is acyl and other is alkyl radical. After decarbonylation, this 1,4-biradical either cyclizes to cyclobutane or it is cleaved to give two molecules of alkene. And the fission or cleavage to this alkene or ethylene is more efficient, as this cyclobutane is less stable. There is another example. It is a symmetrical ketone, and this bond is broken down, is cleaved, and the decarbonylation 1,4-biradical is formed. Here there are two possibilities, and one is the possibility of alkene formation 1,3-diene. It is 1,3-diene, or other is the formation of alpha beta unsaturated carbonyl compound. Here is another example. Here it is the unsymmetrical ketone, so this bond will be broken down so that the more stable free radical is formed. Then in the next process, decarbonylation takes place, and here are the two free radicals and this cyclopropane ring is also unstable, so that the 1,3-diene are formed. One is a minor product, other is a major product. Here is another example. After decarbonylation, 1,4-biradical is formed. Then the 1,3-diene is formed by cleavage of this cyclopropane ring. Alpha cleavage is not only given by a cyclic ketone but other cyclic compounds such as lactone. Here it is a cyclic ester, that is lactone, or sometimes lactams or cyclic anhydride also undergo alpha cleavage to give biradical. Here one possibility is this, the cleavage of this carbon-carbon alpha bond cleavage, which will give the unsaturated aldehyde. If this carbon-oxygen bond is broken down, then the intermolecular hydrogen abstraction will give us dicarbonyl or dialdehyde. Here this hydrogen is abstracted by this acyl radical, so that the dialdehyde is formed. And at the last, alpha cleavage given by cyclobutanones. Cyclobutanone undergo the similar type of cleavage, which is in the singlet state, to give an acyl and alkyl radical. After decarbonylation, there are two possibilities: either the cyclization, as we have seen in all the previous example, that is the cyclopropane formation, or the alkene formation. And the second possibility is that the beta cleavage and the formation of ethylene and a ketene. Here, if this bond is broken down or cleaved, and then one component is ketene as shown here, and the other is alkene. And sometimes there is a third option, which is the ring expansion and the formation of a carbene. It is only possible if there are some trapping agent like polar protic solvents. So this CH2 here, this bond is broken down and a bond is formed between this CH2 and oxygen, and a pair of electrons will come onto this carbon to form a carbene, which is more specifically called as oxocarbene. In the presence of alcohol, it will give acetal. In presence of a trapping agent like 1,3-butadiene, it gives us a 3-vinyl cyclohexanone after ring expansion. And that's all about Norrish type 1 reaction. Thank you.